What if I told you that a single, really elegant idea could take a slow, clunky solution and make it lightning fast? Well, in coding interviews, that's exactly the kind of leap that gets you noticed. Today, we're going to master that idea, the two pointers technique. Okay, let's get right into it.
First things first, we need a problem to solve, right? And we're going to use an absolute classic, a real favorite for interviewers. That's just perfect for showing off what this technique can do. And here it is. You might know it as the two-sum problem, but with a critical twist. The array is already sorted. Your job is to find two numbers in this array that add up to some target value. It sounds simple, but how you solve it is what really separates the good from the great.
Now, the first thing that probably comes to mind is, well, just check everything. You grab the first number, you add it to every other number. Then you grab the second number, do the whole thing again. I mean, sure, this works, but it is incredibly slow. We're talking nested loops, which gives us a time complexity of O of n squared. For any decent-sized array, that's just not going to fly.
So yeah, let's just ditch that slow way and bring in the star of the show. This is where the magic happens, and we turn that sluggish, nested loop mess into a super sleek, single-pass solution. The two pointers technique is, pretty much what it sounds like. We use two markers, two little pointers, to keep track of our position in an array or a string. So instead of checking every single combination, these pointers work together, intelligently shrinking the search space with every single step.
And honestly, this is the best way to visualize it. Just imagine that sorted array is a number line. Now you put one finger on the smallest number, way over on the left, and another finger on the biggest number, way on the right. This setup, this is the entire key to the whole trick. Okay, let's walk through the logic here. You start with your pointers at opposite ends. You add up the numbers they're pointing at. So is the sum too small? Well, to make it bigger, you have to move your left pointer to the right, toward a bigger number. And if the sum is too big, simple. You move your right pointer to the left, toward a smaller number. You just keep doing this, closing that gap between the pointers until you either hit the target or the pointers cross each other. It's really that straightforward.
And this is the payoff. We've gone from checking every possible pair to just making a single pass through the array. Every step brings our pointers closer together, so we only have to look at the data once. That's linear time, or O of n. Just a massive, massive performance boost. Now let's see how this concept really opens up, because a two pointers technique is definitely not one-trick pony. This basic idea of using coordinated pointers can be adapted to solve a whole bunch of different problems. So the pattern we just saw, starting at opposite ends, that's just one flavor. You can have pointers moving in the same direction, maybe at different speeds, or you can even have pointers that live in two different arrays entirely. Let's check out a couple of these other patterns in action. I'm sure you've seen this classic palindrome before. Figuring out if a string reads the same forwards and backwards is a perfect job for two pointers. So for this one, we use a bidirectional scan. You stick a pointer at the very beginning of the string and another one at the very end. You check if the characters match. If they do, great, you move both pointers one step closer to the middle. You can also just cleverly tell them to skip over any punctuation or spaces. If your pointers meet or cross without ever finding a mismatch, boom, you've got a palindrome. All right, let's look at a different pattern. What if you have two separate arrays, and they're both already sorted, and you want to merge them into one big sorted array? This one uses a parallel scan. Think of it like you've got two conveyor belts. You put a pointer at the start of each one. You look at the two numbers your pointers see, and you just pick the smaller one to add to your new merged array. Then, and this is the key, you only move the pointer for the array you just took a number from. You just keep doing that until one array is empty, and then you just tack on whatever's left from the other one. Okay, so this is the crucial part. We need to understand why this works. It feels almost too simple, but it is guaranteed to find the right answer. So what's the secret sauce? This is the question an interviewer really wants you to be able to answer. It's not just about knowing the steps of the algorithm. It's about understanding the core logic that proves it's correct. Why can we be so confident moving our pointers around and know we aren't accidentally skipping right past the solution? The magic is all in the sorted data. This property is called monotonicity. Because the array is sorted from smallest to largest, we have an absolute guarantee. Moving the left pointer can only make our sum bigger, and moving the right pointer can only make our sum smaller. So think about it. If our sum is too small, there's absolutely zero reason to move the right pointer. That would just make things worse. This simple, unbreakable rule is what lets us systematically close in on the answer without ever missing it.
All right, let's put this into a real-world context. Knowing the algorithm is great, but knowing when to use it and what its trade-offs are, that's what will really impress an interviewer.
Okay, this slide breaks down a really common interview discussion. For that two-sum problem, if the array isn't sorted to begin with, you've got options. You could sort it first, then use 2 pointers. That costs you O of n log n time for the sort. Or you could use a hash map, which is O of n time, but also O of n space. But on an already sorted array, the 2-pointer solution is the clear winner on space, using basically no extra memory. Knowing these trade-offs is absolutely key.
So let's wrap this up. 2 pointers is your go-to move for sorted arrays when you want to get rid of slow, nested loops. It gets you that blazing fast linear time performance with practically zero memory cost. And remember, it's not just one algorithm. It's a whole family of patterns. But most importantly, when you use it, be ready to explain why it works. That concept of monotonicity, that's your golden ticket. And that's really the heart of it. Now that you've got this powerful tool in your toolbox, the real question is, where else can you apply it? Think about all those problems you've seen that rely on that brute force, nested loop approach. Which one of them could you completely transform with this elegant linear time technique?